So this setup we see here where we have a pulley, one section is sort of supported by the table and one is not, is sometimes called a modified Atwoods machine. So on this modified Atwoods machine, we have a 1 kilogram mass and a 4 kilogram mass, and they're attached by a string. So that would mean if this small one is 1 kilogram, I'm going to have 10 newtons of force down on it, which will pull the other block through that pulley. So this one is going to have 40 newtons down on it, which means this one has 40 newtons up. But if it's attached to that 1 kilogram block on the pulley, it's getting pulled forward 10 newtons. That's just the basic setup. But now in part A, I'm given that the coefficient of friction is 0.2. So if FF is equal to mu times F of N, well, I can use that to find this force of friction. That force of friction that opposes the motion will be dictated by the normal force and the coefficient of friction. So the force of friction is going to be that 0.2 for the coefficient of kinetic friction, because we're going to assume it's moving. If it's accelerating, multiplied by 40 newtons, which gives us a force of friction of 8 newtons. So I can see visually from my diagram that if this is the case right there, my F net is 2 newtons to the right, because there's 2 extra newtons pointing right than there is pointing left. So if F net is equal to M times A, then 2 newtons is equal to my total mass. So this is the part that's tricky. The whole system accelerates together, and the whole system is 5 kilograms multiplied by my acceleration, which gives me an acceleration of 0.4 meters per second squared for part A. So this is 4 kilograms, and this is 1 kilogram, and they shift together because one can't move without the other. So that's why we use 5 kilograms there. So in part B, we want to know, well, what if there's no motion because it's the static coefficient of friction that we're being talked about? To have no motion, I need 10 newtons for my friction because I need it to be balanced. I need it to be in static equilibrium. So if I need a force of friction of 10, well, that tells me 10 newtons is equal to this coefficient of friction we don't know, but the normal of that block is still 40. So for this block over here to not move, we need at least like 25% of the normal force to get turned into static friction, so minimum. Now, this is where friction is a little weird. A higher coefficient of friction would obviously provide more friction. So if this is higher, we still have 10 newtons of friction because friction can only kind of rise to the occasion and meet the tension from the other side. You can't have 12 newtons of friction to the left if there's only 10 newtons of friction to the right. So even with a higher coefficient of friction than 0.25, we can't get more, because then that would give us an F net in the opposite direction, and that doesn't make sense based on our definition of friction. So that's where we say it's 0.25 minimum. Anything else would also work, but the force of friction would stay 10.